Find a real root of the function f of x. In this problem, a quartic function f of x is provided. A quartic function means its largest term is raised to the fourth power, and that means the function can have at most 4 real roots. For this problem, we'll determine the roots of the function f of x and choose a solution with the closest real root. If we don't have access to a graphing calculator, we can solve the fourth degree polynomial by hand. To begin, we'll expand the linear and constant term. This quartic equation is said to be in an undepressed form. First, we'll want to transform this function into a depressed form, which will drive the cubic coefficient to 0, and ultimately make the problem easier to solve. We'll begin by assigning lowercase variables a, b, c, d, and e to the coefficients of the undepressed function f of x. Next, we'll substitute y minus b divided by 4a for x. After plugging in 1 for a and 8 for b, we'll substitute in y minus 2 for x. And after simplifying, we have the depressed form of the function f of x, which lacks a cubic term. Next, we'll assign variables uppercase a, b, and c to the quadratic, linear, and constant coefficients. Then, we'll subtract by from each side of the equation. Next, to complete the square on the left-hand side of the equation, we'll add the quantity 2 times the square root of c times y squared minus a times y squared. Next, we'll transform the left-hand side to equal the quantity y squared plus root c plus z squared, where z is a new variable we're introducing to help us solve for y in an upcoming step. To arrive at this left-hand side value, we'll add 2 times the quantity y squared plus root c times z plus z squared to both sides of the equation. Next, we'll plug in the variables a, b, and c, and we notice the left-hand side is still a perfect square. Therefore, we'll find a value for variable z, which makes the right-hand side of the equation a perfect square as well. Then we'll be able to solve for y, and then for x. Since the right-hand side is simply a quadratic equation, it will be a perfect square if there is a double root, which means the discriminant b squared minus 4 times a times c equals 0. After plugging in a, b, and c from the quadratic equation, our resulting equation is 0 equals minus 8z cubed minus 96z squared minus 256z plus 120. Now we have a third degree polynomial to solve. To do so, we'll employ the rational zero test, where the root z may be equal to the quotient of p over q, where p is a factor of the constant coefficient, and q is a factor of the coefficient of the leading term, which in this case is the cubic term. Next, we'll list out some of the values for p and all of the values for q. According to the rational zero test, a possible root z may equal -2 or 1.25 or any one of the number of different possible quotients based on the values of p and q. Once a prospective root z is chosen, it is plugged into the cubic equation and is only a root if the right-hand side of the equation solves to 0. After trying a few possible roots, we determine z equals -5 is a root to the equation. To confirm minus 5 works as a root, we'll plug in minus 5 for z, and it turns out the right-hand side of the equation reduces to a perfect square, and the left-hand side of the equation simplifies to the quantity y squared minus 3 squared. If we take the square root of each side and put all the variables on one side of the equal sign, we're left with a quadratic. Using the quadratic equation, we determine y equals negative 0.28 and 2.73. Earlier in the problem, we defined x to equal y minus 2. Therefore, two real roots of the function f of x are minus 2.28 and 0.73. Although there may be two other real roots to the equation f of x, we'll check the possible solutions from the problem statement, and we notice negative 2.28 is an exact match. And the answer is D. If we decided to also solve for the remaining two roots of the quartic equation f of x, we would divide f of x by the quotient of the two roots we just found, which are negative 2.28 and positive 0.73. The resulting quotient is a quadratic equation, x squared plus 6.449x plus 3.661. The roots of this equation can again be solved using the quadratic equation and equal x equals negative 5.82 and x equals negative 0.63. Neither of these two roots are particularly close to the four possible solutions.